What's up, guys? This is Walid, and today's problem is the radioactivity of thorium. So what we got thorium that has a half-life of 1.913 years, atomic mass 228.0287, and undergoes alpha decay, produces radium, atomic mass 224.0202, has a daughter nucleus. Assume that the alpha particle has atomic mass of 4.002. So what they're asking, what's the decay constant of the thorium? They want the answer in an hour, 1 divided by an hour. Okay, they don't want it by years. They give us by years the half-life. So what we're gonna do is the decay constant is gonna be equal to natural log of 2 divided by the half-life. So that since they want it by hours, you need to change it. So this is 1.913 years. Let me do it right here. Is equal to 1.913 years. Then times 365 days, years, times 24-hour per day. So these cancel, and then you get an answer of 16757.88 hours. Cool. And then you just plug that in here. So decay constant will be natural log divided by 16757.88 hours. So this will be equal to around 4.1362 e to the negative 5. Let's make sure of that. Yep, that's the right answer. Cool. And this is hours. And this one. So what's the percentage of thorium is left after 200 days? So percentage is going to be the n divided by n naught, the initial, divided by the n after certain years. So e to the power negative the decay constant times t. So e to the minus the decay constant, which is 4.136 to the negative 5. This is times, they give us 200 days, and the decay constant is 1 divided by hour. So times 200 day, and then you get to multiply it by an hour, just 24 hour divided by day. The whole thing is to the power, so the hour is going to cancel, the day is going to cancel. So n divided by n naught is going to be equal to 80.8899, and the percentage of that is just 88.99. Cool. Alright, this question took me a while to get, but I'll try my best to explain it. So what we have in here is the energy released from a decay of 10 grams of thorium is used to heat 3.8 kilograms of water. Okay, so assume all the energy goes to water. What's the change in temperature of the water after 1 hour? Okay, so the thing we're gonna do is we need to find the energy released. Fucked it up. Released per reaction. Per like each molecule reaction. Okay, so the way to do that, we need to use E equal mc squared, and then by doing that we need to find the mass. Okay, so the mass we need to find per reaction is 228.02. Okay, minus, let's put the full number actually, 0287 minus 224.0202 minus the alpha particle point 0.02603. And this for this guy came up to 0.00589 U, which is U is the same as grams per mole. Okay, so where they get these numbers? The thorium changed to where did it go? Radium, okay, which has this mass, and then with this reaction we had an alpha particle that came out. So we add all the masses, and the mass that's left is this guy. So this mass is going to change to energy. So E is going to be equal to 0.00589. Okay, that's in U. And then we can change that to kilograms, 0.66 times 10 to the negative 27 kilograms per U, because each U has this amount of kilograms. And then times 3 times 10 to the 8 squared. Cool. And that will give us 8.8101 e to the negative 13 joules. Okay. You can use any units you want. You can use like MeV divided by C squared, but I just make it, as simple as I can, so I keep it in joules. Okay, that's easier for me to get. So this is the energy per reaction, per molecule reaction, going from molecule of thorium to molecule of radium. Cool. So what we're gonna do is we need to find N naught. So to find this guy, we have 10 grams of thorium. So 10 G of thorium grams divided by 228.0287. That's the atomic mass, which is grams per mole. Okay, and we multiply it by 6.022 times 10 to the 23, and this is molecule, or we can put particle per mole. Okay, so when this is going to go to the top, so you can cancel this with mole, and then the grams with the grams on here. So you're left with molecules, okay, which is particles. So we're trying to find how many particles are in 10 grams of thorium 228. Cool. So for this guy, I got 2.6408 e to the 22 molecule, just or particle. Okay. All right. So we have the N naught, how many particles initially there was in the 10 grams. What we need to find now is the N, the N naught, okay, the N after 1 hour, okay, so N after 1 hour. Okay, and if you look back at the question, exactly what we need to find is how many particles, the difference in particles, so how many particles we lost in this reaction. So what we really need to find is delta N, okay, which is going to be equal to the particles initials minus minus what we have after, okay, which is N. Okay, does that make sense, kinda? So delta N is going to be equal to N naught minus, and then this guy is N naught e to the negative delta, the decay constant times T. Okay, so what we can do is delta N is going to be equal to 1, or let's do it the other way, N naught 1 minus e to the negative alpha decay times T. Okay, does that kind of make sense? Where did they get these numbers from? Okay, so what we're gonna do is the N naught we have is 2.6408 e to the 22, and then times 1 minus e to the negative. Let's find this number, which was, where did it go? 4.136. 4.136, and it was e to the negative 5. Time is 1 hour. Okay, this is in 1 hour, so let me write it in the better way. So this is 1 divided by hour, the units of it, times 1 hour. So these gonna cancel. So for this guy, delta n is gonna be equal to the delta n. I got 1.09226 times 10 to the 18. Okay, so that's how many particles we have. We lost. Okay, particles. So what we're going to do is we need to multiply the numbers of particles times the energy per particle. So 1.09226 times 10 to the 18. So this, I don't know why I did that, times the energy per molecule, which is, where did it go? Joules per molecule. So 8.81. 8.81 or 1 e to the negative 13. Okay, now let me fix the other one. E to the 18. Okay, does that kind of make sense? This is particles. This is joules per particle. So we can cancel particles out, and then we get 9622291.9 joules, the total energy. So now we're going to go back to thermodynamics. So delta Q is going to be equal to mc delta T. So delta T is equal to delta Q divided by mc. C is specific heat for the water, and mass is the mass of the water in kilograms. So 9622291.9 joules divided by the mass. The mass in the question was 3.8 kilograms, and then we multiplied by c. This is not speed of light, this is the 4.186, and for those guys, joules divided by kilogram per Kelvin. Okay, so the kilograms cancel, the joules cancel, and then the Kelvin goes up. So for delta T, we got in Kelvin, we got 60.49 the Kelvin. Okay, but that's delta T, and they want it in Celsius in the question. But delta T for the Kelvin and Celsius is the same thing, because the difference between these two is you add or subtract 273.4, I think. 273.4, I think. Something like that, yeah. 273.15. Okay, you add that to Celsius, so the difference is the same. Cool, so there's a difference. Alright guys, if you have any question, let me know. I hope this clears this problem up, and I'll see you in the next video. Bye. Good luck.